No, no, that's fine. All right, yeah. So I thought we're going to start off with a quick reminder what was shown here, and then we're going to end with the WISP and have an open discussion to that, just to make sure we are on the same page. So we have seen these distributions over the last years quite a lot. These are measurements by Pierre Auger of the muon detectors, as well as from the inclined shower analysis with SD as a function of X max. And as we all know, these measurements are unfortunately not compatible with any model predictions independent of the composition you assume. Ruben and Antonella this morning talked a little bit about that. What was interesting, what was shown by Ruben yesterday, that there's also an apparent shift in the X-max distributions. So if you actually correct for that and shift the X-max distributions, even under those conditions, you still see an excess in data of the muons in Auger. So even this, I think, 20-gram X-max shift, if I'm correct, it wouldn't fix the muon problem itself. So there seems to be some problem at the highest energies. This morning, Antonella also showed those distributions again. These are the UMD measurements as a function of the energy. And what is interesting here, you can also measure higher moments. So the muon fluctuations actually, which are shown on the right-hand side. And while you see in the muon numbers, you see kind of this axis in the data that implies that you have a composition heavier than iron. Actually, the fluctuations nicely line up between proton and iron and agree with our expectations. This indicates that probably the muon puzzle is not related to something that goes crucially wrong in the first interaction or early in the shower, but it's probably an effect in the low energy interactions that kind of accumulates over the shower development, which is an interesting observation here. Then we have seen yesterday new analysis of the Cascade Grande data. In particular, here you see the muon numbers for different zenith regions as a function of the primary energy. And here, actually, if you look into the vertical bin on the left-hand side, the situation is sort of inverted. It indicates that there is a deficit of muons in data, or too many muons in the simulations. Interestingly, these discrepancies differ for different zenith angles, which is interesting because you basically probe different, let's say, muon energies when you look at higher inclined showers. So that might also tell us something about the nature of the muon discrepancies, I call them. And then very interesting new measurements from IceCube. You might be familiar with these colored squares, which are the surface measurements of GeV muons with iStop, where we also see for CIBIT 2.1 actually quite good agreement with our expectation. The data is between proton and iron simulations. However, if you look into the post-LHC models, you see that data implies a very light composition that is not compatible with any other X-max measurements. So there it also seems that the models actually predict too many muons in the energy region of iStop. If you now look into the in-ice muons that Steph presented yesterday, they are consistent between all the models and in agreement within their uncertainties with our expectation. So there actually seems to be some inconsistency within the models between low and high energy muons, which also again indicates that probably the muon puzzle is related to something going wrong in the low energy interactions and not in the first interactions where you produce high energy muons. And then finally, this is a compilation that Karl-Heinz already mentioned. So this is just the global muon data without any shifts, just as reported by the collaborations. But then, of course, we noticed that there are energy shifts between the different experiments in the energy scale that cause apparent shifts in the muon number as well. So you need to correct for that. And these were the distributions shown yesterday by the WISP group after the cross-calibration of the energy scales. And here the reference energy scale is actually the TA Auger combined energy scale from the working group. And I want to finish off. Basically, Ralf already kind of addressed that yesterday in the discussion. Maybe we have to take a step back here and look into smaller groups of experiments that you can actually compare one-to-one. And we sort of started that by looking or by organizing or classifying the different experiments according to their muon contribution in the energy estimator. And the different colors here indicate different contributions of muons in the individual energy estimators. And if you, for example, look into experiments with low muon dependence, like the dark points, for example, Isvhecri and Auger, then you might still get a consistent picture. But I also agree with Ralph here that I don't think we can talk about a global muon axis based on these plots, because it's just not a consistent picture if you consider all of those. Maybe as a last comment from my side, before we open the discussion, I also think this is just the first step. I think we also need to look into other dependencies, like the experiments all measure at different lateral distances, for example. They have different energy thresholds. We are at different altitudes in the atmosphere. I think we need to consider all these kind of dependencies in order to get a one-to-one comparison. This is, I think, also what came up during many coffee break discussions here. And I think with this plot, we should open the discussion or continue with the open discussion here. Yes, I probably have to stop sharing, right? You should probably take the microphone so people online can hear you.
Hello, Professor. I have some question. Can I ask?
Yes, go ahead while we are waiting for Ralph's slides.
Muon plugs, whether South Pole or equator or North Pole, where it is maximum or how it is flux variation. If you take North Pole, equator and South Pole.
Sorry, can you repeat the question?
Muon plugs, how it varies from North Pole to South Pole through equator.
I don't think we have data at the North Pole, so I cannot answer that question really.
Okay. And what about South Pole and equator, where it is maximum?
Well, we don't really have experiments that we can really compare, right? Because at the south, we are measuring in the knee region roughly and above in terms of primary energy and GeV muons and high energy muons simultaneously. There's not really comparable experiment at the equator at this point.
And the second question I have doubt, muon bundles happens, means parallel muons. What is the source for generation of parallel muons?
Well, it's just highly energetic muons in the bundle, which tend to be so boosted that you get this bundle distribution.
Okay. Thank you, Professor. Thank you.
Okay, Reddy, I understand your first question. I think the muons that are being referred to here are those associated with air showers at extremely high energy. So we're not considering muons per se, which are predominantly energy muons. So I think that there is a basic difference there.
Thanks, Sube. So Ralph.
Thank you, Professor.
Yeah, so I made a comment earlier that if you have an inclusive, if you have an energy spectrum and you just look at the ground signal, that you can describe your data with our current simulations very well. And this is a slide that is actually from 2012 from the UHECR conference, from the working group. And I show here the example of TA, and the red lines is proton simulations. Whatever QGS at the time that was used. And it's different ways like angular distribution, azimuths, number of counters in the event. And then, for example, on the right-hand side, you see the number of stations here, the signal into stations at 800 meters and charge distribution whatsoever. If you, I hope I can switch pages, yeah. This should show the equivalent for Auger for 50% proton, 50% iron. And I would say if you compare the two things, it's just a perfect agreement. And we are not talking about a muon excess or something else. It's just working fine. Because if you are on such a steep energy spectrum, things are very forgiving. It's you can easily hide effects. And the interesting part in the case of Auger, we went one step further. And here you have the comparison proton and iron only. Probably a little bit hard to see, but it's working equally well if you look at it on the scale. Now, iron has 40% more muons, at least in the conventional sense, and it's still working. So that's the point I actually wanted to make. It's extremely hard to get the sensitivity to the muons if you look at the ground signal without having another quantity that pre-selects things. Because even in the case of Auger, our detector simulation describes our data really, really very well, whether you choose iron or proton or something else. Only in the second step, you really get this sensitivity when you pre-select energy or something else that you correlate with those quantities. And that's the most impressive, wow, that's the best way to show it. And of course, it's a prejudice from my side. I don't want to say that like Agasa, Sugar, Cascade Grande can't do this measurement. That's not the point. I only want to say it's very, very hard because we know from experience from the other experiments, just working fine. Yeah, so it's very hard to see this, to have the sensitivity.
Thank you, Professor, for your kind information.
Yeah, I agree with that. But in this energy range, we also only have 2 experiments, really, right? So, and yeah. Yes. Yes, absolutely. Okay.
Actually, I would comment on a different point. Let's consider this angular dependence, attenuation, and vertical axis. Imagine we want to correct angular dependence. Actually, it's very hard with high energy muons. They're not absorbed. You see, really, if you want to change attenuation length, the only way with high energy muons, we have to create many more of them to overweight the low energy ones. But this would aggravate I-stop result. You get many more vertical GB muons. This would aggravate Cascade Grande result. Same way. What is the opposite, the alternative? Very simple. If you play with photo-produced muons, they're typically sub-GV ones. They get absorbed like that. If you just make somewhat less these muons, you don't influence much inclined showers. You mostly reduce muon number for vertical showers. You immediately get larger attenuation. You get rid of contradiction with Cascade Grande for vertical showers. You get rid of contradiction with I-stop, keeping the high energy muons intact. And as I actually stressed many times at different conferences, the treatment of photo production now in our shower simulations is, softly speaking, primitive. But it's really something one may and should do.
For the microphone. So I think so that's a valid point too. And I think, Sergio, you or somebody else should come forward with a model to test. Or should develop a model that has more muons, for example, in the electromagnetic part, just to.
I am not paid for that.
No, no, that's not the way how it works. You know, if you want to sell it to us, you will have to work for it. And the point is, so we have made Sybil Star, and Felix is going to talk about it. That's a model that people can show it's wrong. And so I hope people will do that at some point. And if it's, and then we learn something. And it's the same is true for the electromagnetic part. Make a model or give us a better hint how we can make one. It's, or like we can try to enhance the electromagnetic pair-produced muons just to play with it, because I think the overall situation is so complex with the data that and it takes a long time with the simulation cycles. That means somebody has to bring out a modified model, a toy model in whatever version, that we can study the different effects. And ideally in a clean way that one model has one effect, the other model has the other effect, that we really learn something. But it's clear that it takes us like 3 years at least to go through the cycle before we have the simulation for the big air shower race, unfortunately. And so we don't want to have a model that is modified within a year. So, because then all the libraries are wasted energy. And yeah, so in this sense also, I think it's important that we get something to validate or invalidate.
I also think that's important to have progress on the experimental side, actually, because we have seen Cascade Grande has nice Zenith dependent studies. And with iStop, we are also working on that, which right now limited to near vertical events, but I think we can also expand on the experimental side there to be
But that
in a
happens
position to
that
test.
happens in parallel. I mean, it would be
Yeah.
bad if we would stop where we are.
Of course, yeah.
But
Right.
like, let's say if you get EPUS R at some day in the future that Tanguy promises,
ULGCR,
you
right,
could
Tanguy?
yeah, and then it's frozen for at least 3 years. It's then 10 years, okay, Tanguy say. Then it's not wasted time in the libraries and yeah, something like that.
Yes. Super.
I had a comment based on your earlier observation, Ralph. It's, for example, the more recent experiments like TA and OJ have multiple parameters that they are measuring. So I wonder whether it is a good idea to put earlier experiments which either measured a single parameter or did not have as extensive a coverage, because while it's highly desirable to have more input, but do we also introduce more errors into the mix by bringing in less precise measurements, however important they were at the time? But as long as we assume the cosmic rays have not changed their properties in the intervening 30 or 40 years, will it really be helpful? And I think Juan Carlos made the presentation. It was clear that there are larger divergences in, at least in some of the measurements to a untrained eye, it looked to me. So maybe somebody would like to.
Yeah, I agree with Sunil. Yeah.
Well, I agree with that, Sunil. And there's another point which I think Juan Carlos mentioned yesterday. We also, if we take these experiments into account, we also should be able to understand them precisely and do simulations of how the response of the experiments is. And often we don't have that. I mean, for example, if we take, say, the MSU array or sugar, I don't know, and sugar had some technical issues also. So the question is, besides having basically only one observable, how well we even understand that single observables, right? And that's another point I think we also need to think about.
Right. So we already have a lot of problems understanding the well-measured data. And if we add more to it, then I don't know whether we'll make progress.
Yes, I fully agree also. Carlos address that. Any further comment? Yes, Tanguy.
It was shown in Juan Carlos' presentation, but it was, I think, not insist enough that the independent energy scale is really the key in all these things. We say, oh, it scatters all a lot, but it scatters only because the energy scale is different in all these measurements. And that's one goal of, and one thing I would like to see with the WISP working group is actually to correct, not just rescaling the spectra, but to correct bin by bin to have exactly the same spectra. Maybe wrong the spectra, but at least the same one for all experiments. And this picture will be much more clear. So yeah, we should really keep in mind that the muons and the energy are one-to-one correlated almost. And only with the independent scale, you can measure the muons. If you have a contamination of muons, as it's shown here in the energy scale, then the result will be modified. So you can say whatever you want about the propagation, the different type of muons. It's all true, but I think it's all second order compared to the energy scale. And that the problem of this plot yet is still it's just rescaled to 1 point and not bit by bit. For example, the Yakux experiment, you look at the spectra, it goes up a lot, like Agatha. So of course the muon then looks like okay, but if you would have the same spectrum than Auger, then the muons will be like Auger or even more. So it's really the key point here. The energy spectra are still not the same on this plot, so you can't really compare, in fact. Yeah.
Did you want to say something? Did you want to say something?
Yeah, so Tanguy, one part is built in, and that is the experiments are shifted in global energy scale, right? So this version did exist already from the WISP group where and now you say you want to do it bin by bin, but that means you assume you know the correct spectrum, and some people either got it wrong or something. So I don't know whether you are allowed to do that, yeah?
No,
Because some people do let's say the resolution correction, other people maybe not. And
Yes.
I don't know. So it's very hard to try to fix the data afterwards, yeah.
of course, but at least, I mean, we won't know if it's the correct spectrum, but at least it would be the same for all experiments, and then it would be less scattering. That's one point. I mean, that's, for example, yeah, I'm sure all this, like your cruise, I'm 100% sure. There was, which was the other one we arrived late? Avrapak, yeah, I'm curious. I think we tried to get it, but it was not so clear. So easy to get the spectrum. So yeah, the picture will change for sure. And of course, like here, I mean, the absolute scale you don't know because you have the mass correction. It's not corrected for the mass here, but you depend on the, like we were discussing, this is encore at the highest energy between OG and TA. This is completely arbitrary. If you with the GSF encore that satellite, it will shift in some direction. So that's no, there is no absolute measurement, but the slope of this evolution compared to one reference model that we believe is kind of okay will tell us something already.
I think sooner.
Yeah, this is just a historical remark. You know, we talked about earlier experiments, and I had worked with scintillators which were used by John Lindsley. They were 10 centimeter thick, almost opaque. And I mean, it would have been a real challenge to calibrate them, have any sense of uniformity and things like that. So I think when you compare with what we have today and the challenges which were faced at that time, those scintillators, by the way, were used in Cygnus experiment at Los Alamos, which was precursor to Milagro, which is a precursor to Hawk. So it was really, I think we need to really think about it, how to combine the old data.
So this comment regarding your question, your comment now regarding the energy spectrum. If you make an analysis and take into account the ESF, for example, correction and the OE correction, you know that these both spectra are completely different. For example, with the high energy regime, and if you repeat the analysis, for example, for Cascade Grande, then you will find that the effect is not too big, not too large. So it is more important the energy scale than the shape of the different energy spectra. So you can take into account these shifts, energy in each energy beam, and it will be a second order effect. The most important one is just to set the energy scale.
Yeah, I'm pushing for that.
Yeah.
No, it really depends of each experiment. I mean, for the modern experiment, you're right. Yeah, but for Avrapak, Yakux, all these points which actually makes the plot looking very bad. This is not true. I mean, you look at the Yakux spectrum. It's not compatible with OG, TA, or whatever. It has a different slope, so you could at least correct for the slope like we do between TA and OG. But no, what you said is correct for Cascade. I mean, Cascade will remain maybe something like we don't know. But for others, I think a big part of the difference comes from this. Yeah, and yeah. I don't know if we could find, maybe I can try to find the Yakut spectrum, but it's really clear that it's not the same one. No? It doesn't. It's not enough to fix a point.
Exactly. I mean, Tanguy, I agree. I mean, it's. I mean, something in between. I mean, it's not a single factor between the energy scales, but also, I mean, bin by bin is something difficult. But there are
no, maybe a trend.
Non-linearities, of course, and we see that, as I say, I mean, also between OG and TA. So that it needs more investigation also.
Or Tanguy, if we follow your spirit, if the spectrum doesn't agree, we shouldn't look at the muons.
Exactly. Yeah.
So we could like use the spectrum as a let's say criterion to say, well, we can combine it or not, because if the spectrum is not even with a shift not coming into the shape of the other spectra, we have to assume something went wrong in the measurement, and nobody can tell us that the muons were then right.
Yeah, this could be another way. Yeah, easier.
Which is quite a bit unfair thing, but you know,
Yeah.
Sergey, on that?
Just to keep people relaxed. With Hevera back, the story was really interesting. I don't know if many people remember. It was one of the experiments we reported the maximal number of flicker events at the time. Something like 15 or so. At the time, they reported something like more than a dozen Uhekra events. And then they did an analysis because this was obtained using, at this time, Mocha, and then they used QGL, and none remained. Really, I think the calibration probably depends very much on needs.
Indeed, yeah, sure.
So maybe let me ask if there are any comments or contributions online, the participants. Because I
wanted to add that it's probably, of course, the dominant part is the energy scale, but here you are putting together, or we are putting together experiments of very, very different quality. Just because they were done 40 years ago. I mean, I don't want to criticize all the experiments, of course, but to put together, there are experiments in which you cannot even find a study of the systematics if you read their papers. So to me, it's really difficult to believe in their output, because maybe it's right, I don't know, but since we cannot judge the accuracy of the measurement, this is something that has to be taken into account. So it would be also good to make a selection there, at least out of curiosity, to see if you select experiments where you can really judge the accuracy of the measurements and see what happens to these plots.
Yep.
Yeah, I have a comment / question, and you'll forgive my maybe naivety and the fact that it's probably an obvious comment, but it kind of follows up with what Antonella just said. We have nowadays 2 experiments in the ultra energy domain. It's TA and Auger. I'm a bit surprised that there's only 1 data point for TA on these plots and for a single model. So is there anything that can be done in that regard? Because Auger and TA could be maybe more easily compared in that.
I would comment because the TA point is really very specific. They saw this kind of muon access at huge distances, 2-3 kilometers. And you see at these distances, you are extremely sensitive to LDS, to special effects in LDS, in the tails, like tails of petit district. How accurate these tails are described by Monte Carlo to large angle muon scattering, which is never included in shower simulation, and things like this. It's really different. So I wouldn't seriously consider this. Let's say we don't have enough accuracy to predict muon signal at few kilometer distance from the cloud. These are really very rare events. We don't have the accuracy of quantum electrodynamics for that.
Telescope array, really not a muon experiment. It's mostly an electromagnetic experiment. To get muons, you have to go to very inclined events. If you're Auger and you go to horizontal events, the detectors look almost the same as if you're looking vertical. If you go to TA, the detectors become basically invisible, right? They're 2 centimeters thick. You're not going to do it. So there's some compromise between invisible and highly inclined, right? So you can make some measurements, but it's not designed for this. Ideally, we would have buried muon detectors, and those were proposed, just not funded.
Just maybe a comment that people, I mean, we forget that was that done 10 or maybe almost 15 years ago by Javier Gonzalez, that the 27% offset in the energy scale of TA is actually compatible with the missing muons in QGZ 2.3, which was used at this time. So in fact, it is sensitive, but as you said, it's difficult to make the difference between electromagnetic and so. Yeah.
You touched really a very painful point. This mismatch of energy calibration is the same in AG and TA. For this very same reason, people decided to calibrate SD by FD. First in AG,
Yeah.
secondly with some reluctance in TA.
Yeah.
Which means it's really, to me, it's the biggest mystery of the cosmic ray studies, that one has this mismatch of the energy scale between SD and not only in TA. In the first place in AG.
Yes, because the models.
It's an unsolved problem, and it remains. In particular, surprising that actually the techniques are different. In AG, there are water tanks, which are much more sensitive to mu. In TA, scintillators, muon signal contributes much less. And then mistress.
Yeah, but
almost exactly the same mismatch of the energies.
So it was this work by Javier Gonzalez that he showed that actually it's not exactly. I mean, it's and then the difference is it actually could be explained in TA by the muons, and it could be explained in OG by the muons too at this time, because it was a long time ago. Now, if you look with different models,
you see, I'm sorry, interrupting you. If it could be explained by the muons, then the mismatch should be different in the two experiments.
No, that was shown by Javier Gonzalez.
Of muons is 10 times stronger than in TA.
That was everybody was saying at this time, and then the game was done by Javier Gonzalez, and it was not what he found. That it actually, indeed, using QGZ 2.3, because it's QGZ 2.3, which has even less muons than QGZ 2.4, that was good enough to explain the difference. Yes,
an energy scale between
it's huge CCR 2010. Huh?
So energy scale between FD and SD never. If I'm not mistaken, some problem with this was already in Agas. It was not really much discussed openly, but there was indeed some problem related.
But I don't know. Is anyone looking with Sibyl Star in the energy scale of Roger? If it changed something? Because indeed there is you have the CIC. I mean the attenuation and so on depend on the number of muons in the model. So I think it's part of the same thing. I believe maybe it's more than that. I don't know, but I think it's the same thing. Yeah. So
maybe that's a good aspect to move over to the energy spectrum discussion.
Perhaps I was thinking it's yeah, I mean, we could move over to the energy spectrum, yeah, perhaps, and then move to the models, because the models, I mean, we could also discuss the models now because it has been directly related. I mean, yeah. So let's go to Antonella if you, yeah, okay. So yeah, thanks for the discussion. I mean, surely we need to continue working in that direction, but I think there's a consensus that we have to be careful with taking everything into account, irrespective of how well we understand the data and what the quality could be at that time. I mean, surely, things have improved over the years, but that level of or that rejection should not be done just after looking and say, okay, we don't like that excess or non-excess of muons, so we disregard that experiment. I mean, it should be on principle basis, and yes, otherwise you induce biases. Yeah. Okay.
All right, we move on to Antonella.
Antonella, yeah. Unless there's something from the Zoom room.
I didn't see.